Okay, so done, or you need one more minute to tell each other what you have learned? You have learned quite a few things, huh? Okay, don't tell me you can't say anything. All right, you should be able to recount a few things, at least 3. So can you tell your neighbor at least 3 things that you have learned? Okay, so very quickly, what do you learn about acid strength? How do we tell acid strength? Okay, so strong acid will undergo 100% dissociation, while a weak acid undergoes partial dissociation. So therefore, degree of dissociation is only applicable to a weak acid or a weak base. So you learn that for weak acid, weak base calculation, we can derive the Ka and Kb expression, right? Okay, so that is our first essential difference. What other things that you have learned about autoionization of water?
Very slight.
Okay, it's a very small extent of autoionization of water, giving rise to 10⁻⁷ of the H plus concentration at 25 degrees Celsius. What else do you learn about water? What else do you learn about water? You learn some other constants, right? You also learn about Kw. So what is Kw? Kw is the concentration of H plus multiplied by concentration of OH minus. That is the ionic product of water. So what does it tell you? What does it tell you? The Kw value can be obtained from data booklet. It's 10⁻14. Okay, so this Kw value equals to 10⁻14. What is the relationship between the H plus and the OH minus concentration for water? Yeah, they always equal. So water always have equal concentration of H plus and OH minus regardless of temperature. Is always true. When you look at water without acid, without base, H plus always equals to OH minus at all temperature, but it's only at pH 7. Okay, 10⁻⁷ at 25 degrees Celsius. All right, so when we describe whether this solution is acidic or alkaline, we always compare the H plus and OH minus concentration. We only compare with 7 provided at 25 degrees Celsius, right? Okay, so this is what we have learned on Monday. Very important. Yeah, so I hope you still remember all this, huh? All right, so this is what we have learned. So from this calculation, from this chart point 4, we learned that Ka of water is very, very small. Okay, it's even smaller than 10⁻14. So with this, right, it means that whenever I have an acid thrown into water, the autoionization of water will be suppressed because it's a much weaker acid compared to your ethanoic acid as an acid strength. Okay, so autoionization of water is always in the background. It's always there because what we are calculating here is always in aqueous medium. So Kw always applies at 25 degrees Celsius, 10⁻14. Okay, so you must not forget it. All right, and you need the Kw value when you are asked to calculate the pH of a base. All right, in acid, for acid, pH of the acid, very straightforward. You don't need the Kw, but Kw becomes relevant when you are asked to calculate pH of a base. Please take note. Okay, then something else that I want you to pay attention to, because one student from the other class asked me this question. Now, if you look at the word example for 2 and 3, okay, notice that in word example 2, we show the acid dissociation simply just H plus and A minus. I can do without water. All right, so if you want to put water there, you can also do so, but then this will become a H3O plus. Okay, so in acid dissociation, with or without water is fine. All right, in contrast, if you are working with a base, then participation of water becomes necessary as part of your equation. It's no longer optional. Can someone tell me why? Why so? Do you notice that when we talk about acid dissociation, water is an optional reagent, okay? But when we talk about base dissociation, water must always be there. Why so? So it's according to your Bronsted-Lowry definition, acid is a proton donor. So on its own, can it donate proton? Yes. Okay, with or without water, acid can give away H plus. But if you look at the definition of a base, what's the definition? It's a proton acceptor. So where does the proton come from? The proton must come from your water. That's why when you write the equation to show partial dissociation of a base, water must come in because it is the proton source. Get me? All right, so remember Bronsted-Lowry definition, transfer of proton. Okay, so in words, it will look something like this. Okay, so today I'm going to go a bit fast. So if I'm too fast, please tell me. Okay, I move on. So let's move on to the next part. So we have gone through checkpoint 4 and 5 already. Okay, let's look at the next part. So next part, right, I will need you to make a comparison, compare and contrast the work examples for 5 and 6. Okay, so example 5 is calculating the pH of a strong acid and strong base. Okay, whereas for example 6, we are working with a weak acid. All right, so I would like you to make a comparison and tell me what is the similarity and differences. Okay, can you do so now? Okay, read the examples on page 16 and 17. Can you identify what's the difference?
acid, weak base, or weak acid won't suppress and dissociate autoionization of water.
Again, sorry.
So is it weak base or weak acid won't suppress the autoionization of water?
It does, it does. I put WA and strong A. Yeah, both weak acid and strong acid.
Base, right? There's no water in the dissociation. Is it from the aqueous?
No, because it's Arrhenius base. It's not a Bronsted-Lowry base. Bronsted-Lowry base, I need a proton source. Therefore, water must be there. Okay, so what is the first difference you notice? What's the first difference? Yeah, so the first biggest difference that you can see between example 5 and 6 is 5 don't require a Ka or Kb because it's a complete dissociation. All right, so therefore Ka, Kb becomes irrelevant. All right, so for the second example 6, right, you see a Ka value because we are working with a weak acid. Yeah, we need a Ka expression. All right, then what is the second difference that you have observed? Now, this strong acid happens to be a polyprotic acid, or rather, it is able to give out 2H plus per mole of sulfuric acid. All right. In the earlier part of this topic, we always say that if it's a polybasic acid, it's always a stepwise dissociation because every H plus, you have a Ka1, Ka2, and Ka3. So there's a total of 2H plus, right? Then logically, there should be a Ka1 and Ka2, which is different. They are of different value. But for strong acid, please take note, the strong acid, the difference in the Ka value are rather small. Therefore, we assume that it will release 2H plus per mole of the strong acid, according to this. Okay? But if it's a weak polybasic acid, then there is a significant difference in the Ka value. So for a weak polybasic acid, we only consider Ka1 in our calculation of pH. So that is the second difference. Okay? All right, so later on, I'll give you an example for you to look at. So for polybasic weak acid, we only consider Ka1 when we calculate pH. For strong acid, we consider full dissociation. Pardon? Yeah, weak polybasic acid. So how do I know it's weak? Because there's Ka value given to you. Yeah. All right. So in other words, right, if I give you Ka values, that will imply this is a weak acid. Yeah. So if it's a weak acid, I only consider Ka1 for calculation of pH. Okay. So in this sulfuric acid, is Ka value given to you? No. So it implies a strong acid. So if it's a strong acid, you dissociate all. No need to consider stepwise. Yes? In this case, this one is 1:1. But if you look at barium hydroxide, right, then it will be 2 mole. This one is also a strong base. It will be 2 mole. There's no Kb given. So there's no Kb given, right? It implies strong base. Huh? Same idea. Same idea. Yeah. So Kb1 only. Yeah, Kb1 only. If it's a weak base, right, but it's polyacidic, then Kb1 only to calculate POH or pH. Can? No. full. So if it's a strong acid or a strong base, right, even if there's more than one H plus or more than one OH minus, it's full dissociation, not stepwise. Stepwise only applies to weak acid, weak base. Okay, any other question?
Why do we only consider first keyword?
Just memorize. Okay. All right, so the next thing that you have learned from here is you notice that despite being a strong acid, this is a strong acid, right, undergoing full dissociation, but then its initial concentration is very low. So low that is comparable to the concentration of H plus from water. Okay, it's even lower than 10 minus 7, which is contributed by your water. So in this case, you can no longer ignore H plus from water. Okay, you must consider or take the H plus from water into account under this context. Okay, so you have to add them up and get the total H plus, then you calculate the pH. All right, so you only do this if the H plus or OH minus released is comparable to 10 minus 7. Can? Right, so usually we ignore them when your concentration is high. Okay? Yeah, less than or equal.
Because it's suppressed, right? That's why you don't usually
Yeah, suppressed. It's suppressed, but it can no longer suppress when the H plus concentration is very low. Suppression is caused by Le Chatelier principle. So if the concentration of H plus contributed by a weak acid or strong acid is very, very low, then it can no longer suppress the auto-ionization of water, according to your Le Chatelier principle. Yeah. Then you have to add, you have to add them up. Same idea.
Water suppress, like water's dissociation.
Okay, so they will suppress each other. So we just take it as we add them up. Okay, we do an approximation. Okay, so let's move on to the next part. Okay, this part I will not go through with you because this is not the first time you look at the ICE table. Okay, so you can look at it yourself. I just want to highlight the use of this. Okay, so there's this calculation over here, right? Comparison made between example 5C and 6. You are told that despite ethanoic acid being a weak acid, when you do a calculation of the pH, you realize that it's actually lower than that of a strong acid, which is illogical because by right, a stronger acid should give you a lower pH. But in this calculation, you see the reverse trend. Okay, so why so? It's because your initial concentration of the strong acid is much lower than that of the concentration of the weak acid. Okay, so in other words, right, what is the important learning point here? The H plus concentration or the pH depends on two factors. All right, they are the initial concentration of your acid. So if you have more acid to start with, of course, it can give more H plus. Logical, right? Okay, if you have a higher concentration of the molecular acid, of course, it will give you a greater source of H plus. Okay, then of course, it depends on the strength. So if it's a strong acid, it will undergo 100% dissociation. Okay, in case you have forgotten, what is dissociation? Degree of dissociation is defined in the earlier part of your notes as H plus dissociated over HA initial. Okay, so that's how we define degree of dissociation. Okay, so what is the significance of this? This means that I can only tell whether an acid is strong or weak by comparing these two. Okay, you need to require the relative concentration of H plus and the acid initial. Okay, to deduce acid strength. Okay, you cannot tell the acid strength purely by looking at the pH value. Or you cannot say, oh, this one has a higher pH value, therefore a weaker acid. Cannot say that. Okay, you need a comparison. Can?
So if I put like very small amount of H2SO4 and I measure the pH, it wouldn't be very low.
Yeah, because it's very diluted. Yeah. Okay, so let's move on. Right, the rest, okay, you read on your own. I just want to highlight the use of this equation. So when we apply Ka and Kb expression in our weak acid, weak base calculation of pH, right? Okay, you are allowed to use this as your shortcut. Okay, so that means you can skip the ice table. If you are fast enough, you don't need the ice table. You just plug in this expression and calculate the H plus and the OH minus concentration. Okay, but this expression only applies, okay, provided that you have equal concentration of the dissociated ions. Okay, for example, if I have X of this dissociated, this is X and X produced. If I have Y of this dissociated, then this will be Y and Y produced. Okay, so because they are equal concentration produced, therefore you can use the square root. So if you look at the equation, right, you use the square root, right? Okay, so where does the square root come from? The square root comes from the fact that you have equal ions dissociated. It's math, it's actually math.
Isn't this always the case?
Huh?
Isn't this always the case?
Yeah, provided you have this. This is not always the case because later on, when you come with buffer solution, things get haywire. All right. So in this case, right, you are allowed to apply this because it's just weak acid. Nothing else is present. Later on, you see a lot of reaction coming in. Okay, it will get messy and very confusing. Yeah. Okay, and also in this expression, right, due to small extent of dissociation, we are going to make such assumption, okay, to simplify the calculation. Okay, so there are two things. You can use a square root and you can do this approximation. Okay, so in other words, these are your initial concentration. They are no longer at equilibrium. Okay, so whatever you are working with here is the initial concentration. Okay, it's a shortcut. Okay, with that in mind, then you can try the checkpoint. Once you are done with this part, you can try the checkpoint now. Checkpoint 6. Yeah. So in this case, because we know that X is very small, so we equate it to the initial. H plus release from so no, we always assume. We always assume. In this calculation, there's also this assumption right here. Okay, it's here. So for weak acid or weak base, this is the assumption we make to simplify the calculation. Initial. Then I put initial. Because we made this assumption. X is negligible.
So what even with molecular is still only these ones.
Yeah, because Ka1 will suppress Ka2.
Is there a reason why we make this assumption, or is it just memorize it?
Usually because the X is quite small. So for this right, you can see that the X is like 10 minus a square root. Yeah, it's a 3 decimal place.
So
It's
it's
like,
equivalent to
yeah, it's like 100 times smaller,
other than that.
the original. So this one is 0.1, right? Whereas this one is 0.001 or 0.006. Yeah, so it's 1,000 times, 100 times difference.
Okay.
Yeah, so it's like only 1% dissociated. That's why we can take it to be the initial.
Oh.
Yeah, that's what we meant by a small percentage dissociation.
Oh, okay, I understand.
Yeah, pH. All pH calculated to 2 dP. Yeah. pH and pOH. Ayo. Okay, are you done? Can I go through the answer? All right, so for the first one, you need to recognize that this is a base, huh? All right, there's a lone pair of nitrogen that can accept a proton from your water. Therefore, it releases the OH minus as a result. Okay, so this OH minus release will be related to the Kb expression. So based on this, then you can calculate. So you just plug in the square root Kb times the concentration of the weak base. So you take this to be the initial. Okay, because usually the percentage that dissociates are rather small. That's why we can make this assumption. Okay, so if you look at the previous example, right, the part that dissociates is actually 1/100 of the original. Yeah. Okay, so therefore you can make this assumption. So as mentioned, right, what you can calculate straight away is the pOH first. Then you need to subtract to calculate the pH. Okay, so when you are working with a base, there's always this additional step involving your pKw. Okay, so let's look at the next part, the acid dissociation. Then it should be quite straightforward. You just let your acid dissociates into 2 parts, H plus. Then you just do the square root Ka. So again, you can assume this to be the initial instead of the at equilibrium. Okay, so when you take it to be the initial, you simplify the process, then you can calculate the value. Okay, everything to 2 dp. You know how to derive this, right? Okay, let's do a quick check. Are you done? Okay, let's do a quick check. So there are 2 questions here. So this is the example that you have seen in the earlier parts of your notes. So for weak acid, right, do appreciate that Ka1 and Ka2, the difference is 10 minus 5. Ka2 and Ka3, the difference is another 10 minus 5. So because of the significant difference in the Ka value, you can see that Ka1 can easily suppress the dissociation of Ka2 and Ka3. All right. So therefore, when you're asked to calculate the pH of this solution, when you're asked to calculate the pH of this solution, you just need to take this into account. While Ka2 and 3 will not occur because of the suppression. Okay, any question?
So you only form H2PO4.
Yeah. So the rest, right, will not occur. So if you have the H3PO4 in water, you only see Ka1 taking place. 2 and 3, none at all. Okay, suppressed. Right? Then one student from the other class asked me, if we are only interested in Ka1, then why do we bother to find out the values for Ka2 and Ka3? Why do we bother? Good question. What do you think? Because you just have to know. So if Ka2 and Ka3 will never have their turn, then why bother to know them? Hypothetical. Okay, so remember, during a titration, later on, we are going to sketch a titration curve. That is the most challenging part of this topic. Okay, so before I go into that, do appreciate that during titration, the H plus will be removed as it is titrated against sodium hydroxide. So as the H plus from Ka1 is being removed, can it still exert LCP on the second Ka2? No. So when the Ka1 is completely removed, you will remove the Le Chatelier principle, the Le Chatelier effect on Ka2. That is when Ka2 starts to occur. Yeah. Okay, never mind. Skip. Okay, so let's look at question number 2. All right, question number 2. What is the pH of mixing HCl solution and ethanoic acid solution in 1:1 ratio, given that their initial concentration is 0.2 mol per dmq each? Don't need calculator. You should be able to tell me the answer. What's the pH value? Okay, what is the first thing that you need to pay attention to? What is okay, it's only 2 sentences. Right, 1 sentence actually. 1 sentence. But there are many important information. Okay, so what is the first thing that you need to pay attention to? What is it? Pay attention to the English. Okay. What English? Ratio. Okay, why ratio? Okay, so equal volume. So what is the significance of equal volume? So is 1:1 ratio important? Yes. Then what is the significance? If you know it's important, then what is the significance? Neutral? Why will it become neutral? Why will it become neutral? So is 1:1 ratio important?
Oh,
No? Yes? No? Yes?
actually not sure. I mean, it should be there for a reason.
Should be there for a reason. So in this case, you also pay attention to the acid strength. Yeah, so you recognize that this is a strong acid, while this is a weak acid. So this means that you can totally ignore the contribution by the weak acid. Agree? So that is the first thing that you should pay attention to, compare their strength. Okay, strong acid is the sole contributor of the H plus. Weak acid will be suppressed. Okay, so initial concentration is 0.2. What is the significance of this? HCl concentration upon mixing. Is it still the same as initial? Is it still the same as initial before mixing? Then what is the relationship? Yeah, it will be half because your total volume is double. Total volume double. So all your mole calculation come in. So if you're weak in mole calculation, this topic you will struggle a lot. Yeah. No joke. Okay. So please take note. In this case, noticing that the total volume has become double. Okay, this means that the concentration will be diluted by half. So you need to multiply by half. So original is 0.2, now is half. It is a 0.1 mole per dm cube. Okay, we ignore the contribution by weak acid. So this is being a strong acid. This will mean that H plus dissociated is also 0.1 mole per dm cube. So what is negative log of 0.1? Still need to punch calculator. Negative log of 0.1 is 1. pH 1. That's why I say no need calculator. Can? So please take note, when you do this tutorial, you need to pay attention to dilution as well, especially when you mix two solutions together. And it's just so that these two solutions do not react with each other. Both are acid. There's no reaction. Later on, you'll see solutions that they react with each other. Then makes it even worse. Okay. Can? Okay, can I give you like 1 minute to digest this?
Can I check this?
Hmm?
So when you calculate the pH, you only consider this because it has a significantly higher dissociation of this, which suppresses the
K1,
this, K2 and 3.
Mm. Yep. 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 Yeah. Negligible. Mm. Yes. How do I calculate? You don't need to know. I mean, when I start titration curve, you will calculate. Okay, even if I go through now, it doesn't make any sense to you. Okay, all right, so let's move on. Okay, so this one you can read on your own. So remember, conjugate acid-base pair of a weak acid or weak base, they are a very loving couple. So if you start off with the weak acid, it will react with it will dissociate in aqueous medium to give you the conjugate base. Okay, so if you have conjugate base to start with, it will react with the water to release the weak acid. Okay, so they always coexist with each other since they are a very loving couple. All right, so if you look at the Ka expression, H plus is released here, so Ka expression will be as such. So when your conjugate base reacts with water, OH minus is released. So Kb expression will be as such, right? So you notice that when you multiply the Ka and Kb together, this and this will cancel, this and this will cancel. Then you end up with only concentration of H plus and OH minus. And what is that? Your Kw. All right. So Ka times Kb of a weak conjugate acid-base pair will be equals to Kw because we are always working in aqueous medium. So therefore, this always apply. And Kw is equals to 10 minus 14 at 25 degrees Celsius. Can? Right, so can you help me put this in to remind yourself the relationship pKa plus pKb equals to pKw only applies to weak acid and weak base. Okay, it doesn't apply to strong acid, strong base. Anyway, strong acid, strong base doesn't have Ka and Kb. They don't have, right? Can? All right, so with this in mind, then we have this, which you can read on your own. Read on your own. All right, let's come to section 6. All right, section 6. All right, so for acid-base equilibria, the salt that you're working with must be soluble. Okay, it must be a soluble salt. Okay, so when the salt can dissolve, then we consider hydrolysis. Okay, the salt must dissolve first, then we consider possible hydrolysis. So for acid-base equilibria, it's all soluble salt, all soluble salt. Later on, you are going to learn another equilibria. That equilibria is called solubility equilibria. So in this solubility equilibria, right, what you're dealing with is sparingly soluble salt. That means it's insoluble, majority. Yeah, okay, so for this one, right, in this context, fully soluble. Okay, can read on your own, read on your own, read on your own. Wow, very happy. Okay, let's come here. Let's come here. 6.5 table. All right, so 6.5, this table is a summary of what you're supposed to gather from the notes. All right, so when you have a salt which is fully soluble, how do you represent it in the equation? You have the salt over here, placed in aqueous medium, then it will form the cation aqueous and the anion aqueous. Okay, so this is how you will write how the salt dissolves. Full dissociation. Okay, so what is the thinking process? Okay, sorry, I think I'm too fast. Okay, so what is the thinking process? I would like you to copy this down. Okay, so once you look at the salt, the formula of the salt, you must recognize that the base forms the cation while the acid forms the anion. Okay, the rest you copy first. Okay, more or less done. All right, so what do I mean by this? Check which parent is stronger. Okay, so the parents, who is the parent to a salt? The acid and base that forms a salt, right? So the acid and base that forms a salt are the parents. Okay, so the parents, when the parents are both strong acid and strong base, there's no dominant gene or recessive gene. Most of you do bio, right? So there's this dominant gene and recessive gene. So both are dominant, they neutralize each other. Strong acid, strong base will give a neutral salt, neutral baby. Okay, but if you look at the parents having a strong acid and a weak base, then the dominant gene is the acid. So therefore, it will give rise to an acidic salt. Okay, so if you have a salt, the parents are strong base, weak acid, then it will be a basic salt. Okay, it follows the gene of the stronger parent. And
both strong will be neutral, and then both weak will be neutral.
yeah, so weak, we don't consider them. Yep. Okay, so weak acid, weak base, salt, out of syllabus. We don't need to consider. Can? Right, so with this in mind, so let's look at this, So if you look at sodium chloride, let's practice with sodium chloride. This is my salt, right? My salt will give you, upon full dissociation, giving you a sodium plus and a Cl minus. So what is the parent? So remember, the parent cation, the cation comes from the base parent. So this must come from sodium hydroxide, which is a strong base. Agree? Then your Cl minus, right, comes from the acid. So it comes from HCl, which is a strong acid. So having a strong base, strong acid as a parent, the salt is neutral. Get it? Okay, so if we look at ammonium chloride, let's focus on ammonium chloride first. Ammonium chloride will dissociate in water to form ammonium cation and the chloride anion. Agree? Okay, so this comes from your base. So how do I get the formula of the base here? Remember, the conjugate acid-base pair only differ by 1 H plus. So if I want to reverse, okay, I minus a H plus, this is my base. Okay, so my original base has a lone pair on nitrogen. Therefore, it's a weak base. Okay, so Cl minus must come from HCl, right, which is a strong acid. So who is the dominant parent? Strong acid. So therefore, the salt form will be acidic. Can? All right. So if you look at the next one, ethanoids, sodium ethanoids, when it dissociates, okay, it will give you ethanoate ion and your sodium plus. Agree? Right? So where does this come from? Anion must come from an acid. So what's the acid? Ethanoic acid. Ethanoic acid, strong acid, weak acid? Weak acid. All right, sodium hydroxide. But sodium plus must come from the base. So what is the base? Sodium hydroxide is the base here. So this is a strong base. So strong base, weak acid, basic baby. All right, the baby they produce is basic in nature. Okay, Ken? All right, now acidic means what? Okay, so neutral, nothing to say lah. There's no equation to talk about neutral salt. But when you have acidic salt, for example, ammonium, okay, remember, to give acidic salt, it must undergo cation hydrolysis. Cation must undergo hydrolysis. Positive charge produce H plus. Okay, all right. So when this cation undergo hydrolysis, it will dissociate to form ammonia and H plus. So remember, conjugate acid-base pair of a weak base. They are a very loving couple, right? So this one is from a weak base. So it will give out the H plus in aqueous medium to coexist with its lover. Okay? So H plus is released as a result. Because of the H plus released, it is acidic. Agree?
A bit fast.
A bit fast. Okay. So to release H plus must come from cation. Cation is a plus, right? H plus. Plus give plus. Okay. So this cation is your ammonium cation. So how to give H plus? Dissociate lor. Okay, to give the H plus. Agree? Yeah. So basic means OH minus is released. Agree? That's how you describe a base, right? It releases OH minus. So where does this OH minus come from? Must come from your N ion. N ion is minus. N ion is minus. It will be responsible for giving out OH minus. OH minus. So where does this OH minus come from? Remember, this is the base. Base need water to be around to exhibit the basic property. So because OH minus is released, hence is a basic salt. Can. Yep.
Acidic just means that there's more H plus than OH minus.
Yeah, in the water, yeah.
But that's over.
Yeah, coexist because it's in aqueous medium. Can? The anion hydrolysis. Anion hydrolysis. Conjugate base of the weak acid. This conjugate base of a weak acid. So what is a weak acid? HA, right? What is its conjugate base after losing H plus? A minus. So this is the conjugate base of the weak acid. Yeah. Yeah. Yes. Okay. Okay, so let's look at this. So ammonium chloride is one example of strong acid weak base. So please take note, a weak base can also come from a metal hydroxide. And for metal hydroxide, it's likely to be N equals to 3. Can you help me put this in? Okay, so weak base can be a nitrogen as a base using the lone pair of nitrogen. So that is a weak base. So that is one category. Second category of weak base is you have a metal hydroxide, whereby it's a 3+ charge. Huh? No, 3+ is the extreme one. We look at the extreme. Okay, so in this case, right, one example, if you have done chemical periodicity, you should know that AlCl3 is acidic, right? Yeah. Okay, so this is a salt. This is a salt. So upon full dissociation, it will form Al3+ and 3 chloride. Okay, so what is this cation must come from where? Come from a base, right? So can you tell me what is the base that form this cation? Yeah, AlOH3. Then the chloride must come from HCl. So this is your strong acid. This is your weak base, right? So weak base, strong acid as parents. This is an acidic salt. That's why the cation undergoes hydrolysis to release H plus. This is what you have learned under chemical periodicity. Okay, all this comes together now. All right, so it must be a 3+. Then got the polarizing power, blah, blah, blah. If you still remember, okay, whatever. All right, okay, so can I quickly go to the checkpoint? I want to finish the checkpoint. Come, let's do this. Checkpoint 7. Yeah, most often 3. The N over there is most often 3. Yep. Cation goes back. Oh, I want to find the parent.
Why do you go backwards when it's a weak base?
How does it go backwards when it's a
Like, why
weekdays?
does it go back to?
Yeah, it does. It's an equilibrium. When your ammonium dissociates, right? I process. Yeah? I show an equilibrium process. So the ammonium after releasing H plus, right? The ammonia can also pick up the H plus to go back to your ammonium. It's an equilibrium process. It's not one arrow. It's a reversible process. Is that what you ask? I don't understand. I don't understand your question, is it? Uh-huh. Huh?
When there's like one strong acid and
Yeah.
weak base.
Yeah. These are the parents that undergo neutralization to form your ammonium chloride.
I think
Hmm?
the weak base
Will be the ammonia. No. So what we are doing here is we are trying to, this is my soluble salt, full dissociation. So I'm trying to work out what is the parent to form this cation. So it's ammonia. Because I say that the cation comes from the base, while the anion comes from the acid. Yeah, so after I split up into the cation and anion, right, I try to identify the parents. So this is the parents. And this is the parents for the anion.
What is this?
Again, sorry.
What do you cation?
Cation, that means I need to account for the H plus. Huh? Acidic salt means is able to release H plus, right? So this is the equation to account how H plus is being released. Yeah, so this is to account how OH minus is being released. Basic salt, right? Basic salt means what? Can give out OH minus, huh? So how do I write the equation? This is how I write. Okay. You have to memorize. That means it's from your, huh? Yeah, these are the more common ones. Huh? Charge size ratio only applies to metal cation, but it's not always a metal cation. Oh, okay. So all right. Are you able to identify the cation and anion? I just show you the cation and anion first. Okay, so the cation here will be. So you have to identify your cation first, identify your anion first. Then you can work backwards to identify the parents. Yeah, so if you have difficulty identifying the cation and anion, please clear it with your neighbor first. If your neighbor cannot help you, clear with me. Yeah. Okay, you must know how to see the cation and anion. Can? Then after that, right, try to work backwards to identify the parents and their strengths. Okay, so can I leave it to you to do this as homework? Because now it's CCE. Yeah.
What is the significance of whether they can undergo hydrolysis or not?
Aiyo. Remember this thinking process. Hydrolysis means reaction with water. So after you have identified the parents, you know what is the nature of the salt, acidic salt or basic salt. So if it's a acidic salt, then the cation must undergo hydrolysis. If it's an alkaline salt, then the anion must undergo hydrolysis. Check your answer. Check with your neighbor first. Check until it's no. Okay. All right. So we'll end the lesson here. So if you got confused, right? Please double check with your neighbor. Then if not, double check with me.
Acidic salt.
Yeah. If it's the acidic salt, it must